And we're going to do that experimentally. So you're going to have to pay close attention here. All right? So this is the experimental setup that we are going to use to understand how the hydrogel works to allow for proteins with a signal to make it across from one side to the other. Right? So the idea was that once people figure out how to make the hydrogels in the test tube, that you could make a hydrogel, all right, put it on a microscope slide, so you can look with your microscope at the boundary between the surrounding liquid and the inside of the hydrogel. So that's what we're focusing on in here. The boundary between the fluid that is bathed in and the inside of the hydrogel. Of course, this is not a donut shape, but it doesn't matter. All we want to understand is how do proteins get into or not into the hydrogel. All right? So if I were to just look with my microscope over here, and just look with bright light, just with regular light microscopy, you will see the image right there at the very top. You will see on the buffer side, it's just black because it's just water in there, okay? And then the gel is over here and looks very solid, all right? And it's white because there's a lot of protein in there, it's reflecting light. So that's what you're seeing here with this microscope, looking at the boundary between liquid and gel. The gel is white, the liquid is black. All right? In there. So now you have the setup. And what we want to do is look at the ability of proteins that are fluorescently tagged, so we can actually see them, to go from the buffer that is on the outside into the gel. So here's one example. So here we're taking a very large protein, doesn't have a signal, all right? It's just a big fat protein that is fluorescently tagged, all right? So it's bright, very bright in the fluorescence microscope, all right? So at time 0 or before time 0, we can't add anything, so there's no fluorescence anywhere, outside or inside the gel. Then after 10 seconds after addition, here's all the protein that you added to the chamber, all right? And see, it's beginning to go into the gel side. So the boundary of the gel is right here. It's making it into that region of the gel. After 55 seconds, it's penetrated even more. 235 seconds, it's penetrated quite a bit. So this protein is getting into the gel, all right? So this is a graph that shows you the intensity of this image right here. So you can see that there's a lot of protein on the chamber, and then there's a diminishing concentration of protein in the gel. So after 25 seconds, after 25 seconds, somewhere in there, you had, the protein reaching all the way up to 100 microns from the gel boundary. Do you all agree with this? Okay, ask me questions about it, because now this is the setup. Now we're going to do the actual experiment. So, questions how this works. Yes?
So only the protein is moving inside this experiment?
Yeah, so we have just one protein and buffer. So the protein, we add the protein in the chamber side. So we add the protein over here, and then the protein is going to start diffusing into the gel. That's what we're seeing here. Yeah?
Can you re-explain the curve of the graph?
Yeah. So this is the boundary of the gel. All right. So it's buffer on that side and gel on this side. And this is the intensity of light, of fluorescence, which is proportional to the concentration of protein. So there's, we start with 100% in the chamber, because it's the maximum fluorescence that we added in there. And then it's diffusing into the gel. So over here, there's very little protein, so there's very little fluorescence. some more protein here, so there's a little bit more fluorescence, and here's the boundary. So it's going into the gel. It's moving in that direction. If we wait a little bit long, if we wait until the next day, then we would have uniform fluorescence everywhere, because it just went everywhere in the gel and is saturated, and everything is equal concentration. So this is essentially a graph that gives you concentration of protein across distance here. Everybody clear? Yes.
In the first like line at 5 seconds, where it's like the 5-second one, where it's entirely all black. Even at the right before the gel, it's entirely black. Is that because there's entirely no protein?
Yes. So this is minus 5 seconds.
Oh, okay.
For the first picture, you turn on the light bulbs, bright bulbs, to see where's the gel, and where there's no gel, you don't see anything, so it's black. So that's that image there. So then you turn off the lights, and then you're going to start looking only at fluorescent proteins. Right? So you're going to look at that, and the first image is taken before you add the protein. So there's nothing in there that fluoresces, everything is black. At time 0, you add fluorescent protein in the chamber side. So if we had like time 1 second or half a second, it would have been all white over here and totally black on the gel side. And then you just start running your camera every few seconds, taking pictures, and you can see with time, more and more protein from the buffer has invaded the gel. All right? So the conclusion is that in these conditions, a big protein without any signal at all, can go into the gel. So it's not an effective barrier. So at the concentration that they use in this particular hydrogel, this gel doesn't act as a barrier for large proteins. Right? So even though it's solid, has holes big enough that this big protein can get across. So how do they solve that? They can solve that by bumping up the concentration of protein in the hydrogel, the nucleophore protein, right? So they went 10 times the concentration. Instead of 0.27 millimolar concentration of nucleoporin, they went to 2-point-something millimolar, make a gel that is much more solid, right? And repeated the experiment. So again, the gel is shown at the top, and now you can see the gel side. Now, if we compare the images, look, this gel is like very lacy, lots of holes in there. No wonder things can get across. But if you make it really solid, very concentrated, now that's a solid mass in there. And when I add the fluorescent protein on the gel side, does it get in? No. 20 seconds? No. 1,800 seconds? Nothing, right? So here's the graph of that. Right? So this is after 1,800 seconds. All the fluorescence is up here in the chamber, and there's 0 inside the gel. So at this concentration, big protein just can't get in. All right? Everybody good with that? So conclusion, at 2.2 millimolar, this hydrogel is good, is an effective barrier. If you subsequent experiments calculated what is the, and this calculations is really hard to do, right? You have to have a lot of assumptions, but what is the concentration of nucleoporins in a living cell, in a living nucleopore complex? And they come up with a number that is close to this, all right? So they think that this is the actual concentration of proteins inside the nucleopore complex, forming that little green hydrogel. So everybody good? So when you have that well-formed gel, a big protein cannot get across. All right? So what about the receptor proteins, the nuclear import receptor? Let me see which is, okay, so just explanation from what we just said. If you make a gel at small concentrations of protein, then you're going to have a lot of gaping holes in there through which a big protein can certainly get across. But if you make the hydrogel at really decent concentration, now a big protein is just going to bounce right back on that little bit of hydrogen. All right? So, yeah, so this is the next super exciting question here. So what they did next was to take the protein that acts as the receptor, the nuclear import receptor in this case. You could do the same thing, it has been done subsequently with nuclear export receptors, and the same thing has been observed. Right? So you take a nuclear import receptor, which happens to be fairly large, 124 kilodaltons. Right? You tag it with fluorescence so you can visualize it. And then you add it to the chamber at time 0. All right? So there's the result for you. So look at this data, talk to your neighbors and see what conclusions can you reach about this experiment with the nuclear import receptor through time. All right? And then we're going to collect conclusions from everybody and see if we have a list of conclusions that we can all agree with. Go. Together here. And I want to see how somebody tried to approach this problem. So to try to read this experiment, how do you read this experiment?
What do you mean? Is anybody else confused by the question?
Okay, so I'm asking you, how do you interpret this data? So
Okay, got it.
say this graph. What is this graph saying? Okay, so always basic skills. Let's read the axis, right? So we have here distance. 0 marks the boundary between the chamber on the left side and the gel on the right side. Right? So it's distance in micrometers from the gel chamber boundary. And then on the y-axis, what do I have? Fluorescence, which is proportional to protein concentration. Right? So I have protein concentration on the y-axis. So what does this graph tell me? That there's what?
High concentration on the gel side.
That there's a very high concentration on the gel side relative to
The butter side.
the outside, right? So you put in the chamber, you put a given concentration that we're going to call it 1, because we're just normalizing, divided by the initial value, right? And the concentration in the gel is much higher than that in the chamber. Does that correspond to the figures? Yeah, so we can see with our own eyes that the brightness in the chamber is nice, but there's a big bright white line inside the gel, and that is becoming wider and wider and is extending into the gel. Right? So what can we say about the protein as it's going from the chamber to the gel? Yeah?
Moving slowly through the
It's moving slowly, okay, so there's a lot of time in just a small amount of distance compared to the old experiment, right? So that's one conclusion, it's moving slowly. Is it moving in?
Yeah.
So, okay, so that's one big conclusion, right? So, unlike the previous protein, which was not an NLS, unlike this protein, this is just regular gel protein. Doesn't have a signal, it's not a receptor. Can it go across at any time? No. And this one is even smaller than the other one that we were looking at, than the actual nuclear import receptor. This is a nuclear import receptor, big, big guy, and it can get into the gel. So conclusion number 1, nuclear import receptors can get into the hydrogel.